All right, so we're going to start lesson 2 here on naming compounds and writing their formulae. Okay, formulae is plural. Formulas is not right, apparently. I don't know. Anyway, okay, what we want to be able to get out of today, because we probably won't get too far today, okay, is simply distinguish between an ionic compound and molecular compound, and then probably look at some simple naming review, okay, for ionic compounds for today. Okay, now, if I have an ionic compound, what makes it up? What's in it?
Metal.
A metal and
A non-metal.
a non-metal. Okay, so an ionic compound is always going to be made of something from the left-hand side of the periodic table and something from the right-hand side. And by the sides, I mean, remember, we have the staircase that divides the metals from the non-metals. All right, so an ionic compound is always going to contain a metal and a non-metal. Okay, so common ionic compounds, things like sodium chloride, okay, things like that. All right, a molecular compound then is going to be made up of two non-metals. Okay, now ionic compounds and molecular compounds are very different, not just in how they're made up, but also how they're held together. Okay, how hard they hold on to each other, okay, and things like that. So that's what we're going to kind of look at here. Okay, so ionic compounds, like we said, occur when a metal from the left side of the table and a non-metal from the right side react to form a new molecule. So if I have a sodium atom reacting with chlorine, okay, then I can get a sodium chloride molecule. Okay, now, in an ionic compound, an ionic bond is formed. An ionic bond is not very strong, okay, because an ionic bond results from atoms that are trying to gain or lose electrons, right? Kind of the purpose of an atom is that it wants to always, and I know I'm personifying a little bit here. Let's get English for the science guy. Yeah, kind of personifying, okay, atoms here, but they're always seeking to have a full outer shell of electrons. And what I mean by a full outer shell is, we got to go back to Bohr's model that we talked about. Okay, according to Bohr, if I have a sodium atom, okay, it has various levels of electrons, which we know is kind of right and kind of wrong, but we're going to go with it for right now because it helps explain ionic bonds. Okay, so in the first shell of electrons, there are 2 electrons. Okay, now how many electrons does sodium have in total? 11. Okay, sodium has 11 electrons. Okay, its first shell can hold 2. Every shell after that can hold up to 8. Okay, so its next shell is going to have 8 electrons, and they kind of do this. They kind of pair up because of repulsion. Okay, that's 10. Its next shell, which can hold 8 electrons, only has 1 electron in it. Okay, all atoms want to have a full outer shell of electrons. So for sodium, to get a full outer shell, what's easier? Find a home for 1 electron, or find 7 more? Yeah, lose 1. Find a home for 1. Okay, that's way easier. It's way easier to ditch 1 electron than it is to go looking for and find 7 more. Okay, chlorine is a perfect partner for sodium because it's the exact opposite situation. Okay, its atomic number is 17. Okay, so if I have chlorine, okay, its first shell has 2, its second shell has 8, just like sodium, okay, and its last outer shell has 7 in it. It wants a full outer shell. What's easier? Find 1 or dump 7? Find 1. Okay, so these two get along famously, at least at first. Okay, so these two things react. They both get what they want. They get their outer shell full. Okay, so sodium dumps off this electron to chlorine. Okay, chlorine now has its outer shell full. Okay, so does sodium because it kind of loses that outer shell because there's nothing in it anymore. Okay, and now there's an ionic bond resulting there from the trading of electrons. It's a trading, it's not a sharing. Okay, so that's how an ionic compound forms. Okay, through this trading of electrons. Now, I don't want you to take this from a social standpoint too much, but what's holding them together now? Yeah, sort of, but they're not sharing it, right? Like sodium gave it up willingly and chlorine took it. From a social standpoint, they kind of both got what they wanted out of this. There's really nothing to keep them together anymore. That sounds horrible. Okay, this is chemistry now, like life. Okay, but they did. They both have what they wanted. They're now both charged particles. Sodium has a positive 1 charge because it now has 1 more proton than it has electrons. Chlorine has a negative 1 charge because it now has 1 more electron than it has protons. But they both have their outer shell full. Okay, so ionic compounds they can dissociate very easily. Okay? And in fact, that's what happens when you dissolve them in water. How easily does salt dissolve in water? Very easily. Okay, so I put salt in water, I stir it up, and the chlorine and the sodium just go. Okay, they split apart, and now that solution will conduct electricity because there are charged particles floating around in it. Positively charged sodium ions, negatively charged chlorine ions. Okay, if I just have distilled water with nothing in it, it won't conduct electricity because there's no charged particles floating around. As soon as I add a little bit of salt, boom, it'll conduct electricity again. Everybody kind of with me there? All right. Okay, so all you really need to know, okay, is that ionic compounds are the result of the trading of electrons. Okay, there's no sharing and there's no strong bond to hold them together. Okay, that's why we have this bond, ionic bond. Taken, not shared. Instead of shaken, not stirred. If you haven't seen James Bond movie, that's how he takes his martinis. Shaken, not stirred. Okay, all right. Everybody okay with how ionic compounds form? Okay. All right, if I want to name a simple binary ionic compound, okay, I write the metal first, then I write the non-metal second. And what do I change the ending to? I. Okay, so I have sodium and chlorine, they go together, I have sodium chloride. Okay, we just change the ending to I, very simple naming procedure. Okay, all right, so the name of a binary ionic compound is the name of the metal and the name of the non-metal. Name of the metal is stated in full, name of the non-metal has an "ide" suffix. Okay, so magnesium oxide, sodium fluoride, aluminum sulfide. Okay, notice all of these are lowercase. The chemical name for an ionic compound is not a proper name. Okay, like John Doe. Okay, that's a proper name. I capitalize the John, I capitalize the Doe. Okay, it's a name. This is not a name. Okay, we call it naming, but this is not like a proper name. So they're not capitalized unless you are starting a sentence with them, like sodium chloride tastes great on French fries. Okay, then you would capitalize the S. Right, but otherwise you do not capitalize the names of ionic or molecular compounds. All right, is that ringing a bell for everybody? Okay. So we have to remember that we name both ions, okay, because we don't want to forget either one, okay? We never capitalize the names, and when we're using formulas, so if I'm writing the formula for an ionic compound, I have to make sure the charges balance, okay? So if I'm writing out the formula for aluminum chloride, okay, I have Al with Cl, okay? How do I know that there's a 3 that's going to go there? Remember what to do there? What do you call that? Nope, not cross multiplying. Well, you get sort of cross multiplying, actually. It is kind of like that. It's called the drop and swap.
Yeah.
You guys heard that before? Okay, I look up the charges of these things on my periodic table. Aluminum is a 3+ charge, chlorine's a -1. So I drop the 3 and swap it. The 3 goes here. The 1 drops, comes over here. We don't write 1s. And I've got my formula. Okay, simple as that. Okay, if you have to, you always simplify as well. If it came out to like 2 and 4, you would simplify it down to 1 and 2. Okay. Ringing a bell? Okay. So if I have aluminum and chlorine together, I have aluminum chloride. I have 3 chlorides here, but I don't indicate that. Why don't I indicate that in the name? Because it's ionic. Okay, I don't need to. There's only one way that aluminum and chlorine can go together and have their charges balanced, and it's this way. So I don't need to write in tri or di or whatever. Okay? There's only one way they can go together. The reason we use prefixes in molecular compounds is the charges aren't being traded. They're being shared. So there's any number of combinations that they can go together as. Okay? But for ionic compounds, because the charges are being swapped, okay, they can only go together one way. Prefixes are not necessary. Okay? Ringing a bell. Okay, speaking of ringing bells, it's like 7 minutes and one will ring. Okay, but we're going to get through a little bit more here. All right, I want you guys to try, let's say, just the first 6. Okay, try the first 6 there, and we'll get through those before the bell goes. Okay, so let's have a look at least the first 3 here for now. Okay, so Na and Cl goes together. Na is sodium, Cl is chloride. Okay, so sodium chloride. Okay, for number 2, K is potassium, F is fluorine, right? So it'll be potassium fluoride. Actually, the U goes first, doesn't it? Yeah. All right, and then for number 3, okay, we've got hydrogen and we've got iodine. So this stuff will be hydrogen iodide. How do I know? Like, hydrogen's a gas. How come it's in this ionic compound if ionic compounds are supposed to have metals first? Yeah, it's still a metal. In fact, it's the most metallic thing there is. Okay, it just happens to be a gas. Okay, it's possible for something to be a gas and behave in a metallic way, and hydrogen does that. Okay, the weird thing about hydrogen is it can actually act as an incredibly metallic thing and an incredibly non-metallic thing. Okay, because its outer shell has 1 electron, it can lose 1 electron, which is what it typically does. Okay, or it can gain 1 and have its outer shell full as well. Okay, because it's only got 2 in that shell. All right, number 4 here, we got calcium and bromine, so this will be calcium bromide. Okay, for number 5, we have aluminum and astatine, so this will be aluminum astatide. And I still say it, aluminum. I don't care that the International Union of Physics and Applied Chemistry says it's now aluminium. I refuse. Okay. All right, and then we have cesium and sulfur, so this will be cesium sulfide. All right, so tomorrow you will have a quiz. I will post it after school today in Google Classroom. Well, not it, but one very much like it. Okay, that you can have a look over tonight, and it'll be on structure of the app. Okay, in the comment here. So make sure you have a look at that tonight. All right, before you go, put your masks on. Okay, and the bell's going to go here pretty quick. Okay, just grab a paper towel, quickly wipe your desk.